In the last video, we looked at a synthesis reaction, and so here's the opposite, a decomposition. In a decomposition, you'll start with one compound, and you'll break it into smaller parts. So you could have the sodium chloride compound that breaks into elemental sodium and elemental chlorine, or you could have a larger compound that breaks into smaller compounds, kind of like this bad boy. This is sodium bicarbonate here, or baking soda, and it breaks down into smaller compounds. Either is still a decomposition. The key with a decomposition is that there's only one reactant. With a synthesis, we formed one product, and now again, this is the reverse. So we'll start with one reactant. Now the other thing that we should make note of is that let's say I want to decompose sodium chloride. In other words, I want to break the sodium chloride bond. In the last video, we mentioned how the sodium-chlorine bond is very stable. The sodium and the chlorine have a full outer shell. There's a transfer of electrons. It's a good thing. If you want to break a bond, you must add energy. Breaking bonds is always endothermic. Whereas the opposite, the synthesis, when you form the bond, energy is released, exothermic. So now if you want to break the bond, you need to add that energy back into the bond. Any bond will require energy to break. These decompositions are often endothermic. In the lab, they're going to ask us, which reaction was endothermic? In which reaction did you need to add heat? Did you need to put something on a Bunsen burner or a hot plate? That's your endothermic change. Now again, often the ones that we'll look at will involve a compound breaking down into its elements. So we could write the equation for the decomposition of iron 3 oxide. Iron 3 oxide. Iron is +3. Oxygen is -2. So I can make that neutral, +6 -6. And if I do the decomposition, I'm just going to break iron oxide into its elements. Elemental iron is just Fe, not diatomic. But elemental oxygen is diatomic. Now again, you can probably estimate the most common error here. People will say Fe2O3 decomposes to produce Fe2 plus O3. We're like, I don't know, just slash that thing in half, right? But unfortunately, elemental iron is not diatomic, and oxygen gas is not triatomic. O3 does exist, it's ozone, but that's not what we're trying to form in this decomposition. So again, those little subscripts do not get a free ride to the product side. We split the compound into its elements, and really all we're checking for is an element that might be diatomic. And now we balance. So my first thought is that I'm going to need 2 iron, right? But then I notice that there's 3 oxygen on the reactant side and only 2 on the product side. And to get that to balance, I'm probably going to need to double the oxygen, because then I'm working with even numbers. So I can get 6 oxygen, but then I'm going to need to change that coefficient of the iron. Now instead of 2, I have 4. And that's why they call it balancing. But it always works. And it's not that bad. Hopefully, as you balance more and more of these equations, it's just coming easier and easier. If the formulas are right, the balancing should be a piece of cake. There, done. And again, we would put the base symbols in. Iron oxide is a solid, it's rust. Elemental iron is a solid. And this is O2, oxygen gas. Done. These are kind of fun, aren't they? If you can predict what kind of a reaction will occur, you can often predict the products. What if we have the decomposition of sodium sulfide? All right, sodium sulfide. IDE is just regular sulfur. Sodium is +1. Sulfur is -2. So I'm going to need 2 sodium to make a neutral compound. This will decompose to form sodium, not diatomic, and sulfur, not diatomic. Well, that looks weird, but it's okay. I mean, it feels like little naked products, just sodium and sulfur, but it's right. And good Lord, this is so easy. If I want to balance this, I just need 2 sodium and I'm done. Sodium sulfide is kind of a white crystalline solid. Sodium metal is a solid. And sulfur is also a solid. I would kind of mention that as we run these reactions in class or in the lab, then we're witnessing the phases. That makes it a little easier. If it's elements, sometimes that's not so bad. Most elements are solids. There are only 2 elements that naturally occur as liquids, bromine and mercury. And the gases are usually things that you're familiar with. Hydrogen, nitrogen, oxygen, fluorine, chlorine. If it's a compound and you're not sure of the phase, very soon, in one of the next couple videos, I'll show you a little chart, a little cheater chart, that you can use to look up phase symbols.